Do you know unrestrained beams are designed for lateral torsional buckling? In this lecture, I will talk about design process for unrestrained beams as per Eurocode 3. This is part 13 of lecture series on steel design. For other parts, please have a look at the link down below. Hey friends, if you're new here, I am Dr. Javed Qureshi, a senior lecturer at a London university. On this channel, we explore technical and human skills to help us lead more productive, happy, and examine life.
What I want to start today is I would like to give you a brief overview in terms of where we are in our design of the steel structures, and then I will discuss today's topic, which is unrestrained beam, so that you understand the big picture, you understand what components of steel design you can design now. I will spend first 6 minutes giving you overview of the topics covered so far, including loading, tension members, compression members, and restrained beams. After that, I will move to the design process for unrestrained beam. Please feel free to move between the topics. Timestamps are given in the description down below. We started with design of tension members, but before we design tension members, it was loading that needs to be carried out. Remember that there are always 3 steps to designing any structure. First, you need to work out loading. Secondly, you need to carry out structural analysis, which means that determine shear force, bending moment, axial forces, tension, and compression. And finally, we design any structure. And the purpose of design of structural components is that we always compare applied versus resistance, or in some countries we call it as demand versus capacity of the section. Demand over capacity is termed as utilization. If demand over capacity is 0.5, then we can say that 50% of the capacity is being utilized. That is termed as utilization ratio. And in all designs, pretty much, we will be doing this kind of exercise. And this NED over NTRD for tension members, this is demand over the capacity. And this has to be less than 1. And when we talk about, in case of columns, again, we will talk about NED over NBRD. And when we talk about restrained beams, we will say MED over MCRD. Again, this is demand versus capacity. This is the utilization ratio that I was talking about. But what we have done so far is we started off with tension members, but before tension members, we learned how to work out design load, which is here. And we always multiply some factors. Permanent actions, it is 1.35. For variable actions, it is 1.5. This is equation 6.10. But we also have 6.10b, where this gamma g factor is multiplied with a factor of 0.925. But the key thing to remember is that design loads have to be multiplied with safety factors. Then we can say that it is NED. Then we can say it is MED. In terms of tension member design, NED over NTRD means demand versus capacity. Utilization ratio should be less than or equal to 1. And NTRD was lesser of these two values, where on the left side, NPLRD was dependent on gross section, and NURD, ultimate resistance, was based on net section, where we took into account the effects of holes. We determined this FY and FU from this table 3.1. And then we talked about classes and why these classes are important. The purpose of classes was to know that what formula to apply. Class 1 sections are very thick and heavy sections. Class 4 sections are very thin and slender sections. There were 4 different classes. And the main purpose of classification was to take into account effects of local buckling on any member. Now, why do we take into account local buckling? It limits the load carrying capacity of a section. So that's why we need to classify the sections. Classification is related to local buckling, and local buckling, on the other hand, is related to compression of plates. If we are applying tensile load, then local buckling does not happen. So that's why for tension members, we did not classify the sections. We limit the width to thickness ratio of individual plates, means flanges and web. And then we compare it with limiting values in the code. So if you have a beam, you consider this left table, and if you have a column, you consider this right table. And in terms of design implications, you can see that bending resistance for class 1 and 2 uses WPL. This relates to the graph over here. You can see that MPL is reached for class 1 and 2 sections. For class 3 sections, on the other hand, plastic moment capacity is not reached. It is less than plastic capacity, slightly above elastic capacity, it means that now we need to classify a section for all member design except tension members. In design of columns, we use reduction factor approach to work out NBRD, and we will use similar approach today in design of unrestrained beams. And then again for columns, we need to determine this phi and alpha. For alpha, you need to refer to table 6.1. You can see that in this figure, this secondary beam can be designed as restrained beam, or it can be designed as steel concrete composite beam. But here we will be designing it as non-composite beam, means restrained beam. So if the top flange of the beam is restrained by positive attachment of the slab, we say that it is restrained beam. We have these primary beams as well, which take point loads from secondary beams. Primary beams are designed as unrestrained beam. It means that top flange is not attached to the slab. Our today's topic will be design of unrestrained beam. But before we do that, I will go through this procedure briefly. So what do we do in design of any beam? We check bending, we check shear, we check serviceability. So bending, again, applied versus capacity has to be less than 1. And again, in case of shear, the utilization ratio should be less than or equal to 1. Additionally, we check this serviceability as well. By serviceability, I mean that you have to check the deflection and you have to compare it with limiting value, which is span over 360. So now I will move on to my main topic, which is unrestrained beams. The design procedure is pretty much similar to column design. I will talk about unrestrained beams, the design procedure, and some examples. The learning outcomes of today's lecture will be that you will learn how to design unrestrained beams today. This is the example of unrestrained beams. You can see that if you have a thin hay floor or wooden floor, then these beams can be treated as unrestrained. Beams bent about major axis may fail in buckling in more flexible minor axis. This form of buckling is termed as lateral torsional buckling. It means that there will be lateral deflection and there will be a torsion as well. And the moment at which beam buckles is termed as elastic critical moment, or MCR.
Lateral torsional buckling is
affected by section shape, degree of lateral restraint, type of loading, residual stress pattern, and initial imperfections. Similar to columns, stocky beams or heavy beams, bulky fat beams, they are unaffected by lateral torsional buckling, and normally we determine their MCRD. The beam, literally, it appears as laterally restrained. So if we have stocky beams, they will be unaffected, similar to columns, by lateral torsional buckling. Now we have two extremes. One extreme is that we have very heavy sections. Other extreme is we have very slender sections where their capacity is closer to elastic critical moment. But most of the time we have this intermediate range where we design the beams. The way we relate elastic capacity of the beam to elastic critical moment is with the help of this key LT. So we use reduction factor approach to work out MBRD, moment, buckling moment, similar to NBRD, buckling axial load in columns, where we use key. Now here it is termed as key LT. I will show you some videos that will make things really clear, but because this video is old, x-axis is termed as major axis and y-axis is termed as minor axis. In Eurocode, y is major axis and z is minor axis. So please be mindful for that. Here they will use y, which means that minor axis.
The next three tests all concern simply supported beams of varying slenderness. A central vertical load, causing bending, is increased to failure in each case. The first beam is just over a meter in length and can be described as being short and stocky. The load is applied to the beam by a screw jack device via a vertical rod. During the loading of this beam, here shown accelerated, deformations are confined principally to the vertical plane, with failure occurring essentially due to the attainment of a plastic hinge at the point of maximum moment. On removal of the load, permanent deformation remains. The second beam is 7 meters long and is much more slender. The load is applied as in the previous test. Observe the response, shown again in an accelerated manner. It can be seen that significant lateral deformation and twisting occur, in addition to the in-plane bending displacement. This is known as lateral torsional instability. The direction of the lateral movement is determined by the initial imperfections present in the unloaded beam. When the beam is unloaded, full recovery occurs, with the beam returning to its original undistorted shape. No permanent damage has been done to the beam, which demonstrates that the failure is elastic in nature and is due to instability. For the analytically straightforward case of a simply supported beam subject to a uniform moment m, using small deflection theory, the equation for the value of the critical moment MCR causing instability is as shown. EIY is the minor axis flexural rigidity, GJ is the torsional rigidity, and L is the length of the beam. Note the coupled nature of the lateral flexural and the torsional rigidities and the absence of major axis properties. For a very stocky beam, the plastic moment is significantly less than the critical moment and instability does not occur. For a very slender beam, the reverse is true and the beam will fail by elastic instability. The response of very stocky and very slender beams is quite clearly defined and relatively simple to analyze, at least in an approximate manner. However, many practical unrestrained beams lie in the intermediate slenderness range, where the effects of elastic instability and plasticity interact. The third beam of this series of tests is just over 2 meters in length and is neither very stocky nor slender. The beam is subject to load as before. It can be seen that lateral deformation and twisting occur, together with plasticity. Removal of the load is accompanied by only partial recovery of deflection, and significant permanent bending remains in both principal planes.
We're trying to target this intermediate range where the plastic capacity and elastic critical moment, both of them, they interact. Again, I would like to show you another video which will tell us about shape of the section.
Observe the response of the two cantilever beams which are of equal length and which have nearly equal major axis flexural rigidities. The one on the left has a high minor axis stiffness, whilst the one on the right has a low minor axis stiffness. Initially, as equal load is applied to each beam, their behaviors are almost identical. However, for the beam with low minor axis stiffness, as loading progresses, instability intervenes. The cantilever on the left does not suffer any instability and would eventually fail by plastic action. Lateral torsional buckling is only likely when a section has significantly different values of second moment of area and is subjected to bending.
This was about the shape of a section, which I'm going to talk about here. I have 4 sections. You saw these 2 sections. One is head section in video and beam section, and we have this flat plate. And then we have tubular sections, square hollow section. All of them, they have same area. And IY means that the ability to resist vertical load. The ability to resist vertical load depends on the depth of the section, because second moment of area is equal to BD cube over 12 for rectangular sections. D has got power 3. So that's the reason we prefer these I sections for beams. Head sections, you can see that their vertical load resisting capacity is only 0.35. And for hollow sections, their load resisting capacity is 0.2. I will have to put 5 times more material than I section to this structural hollow section to be able to take similar loading. So that's why I sections are very economical in terms of resisting vertical loading. Now, how about IZ and IT? IZ is ability to resist horizontal loading, or its ability to resist out of the plane loading, or lateral deflection, ability to resist lateral deflection. So this term is related to lateral deflection. This term is related to twisting. Lateral torsional buckling is composed of 2 terms. One is lateral deflection, other is twisting. So if these 2 things are strong, it means that a section is going to be really strong in terms of lateral torsional buckling. Now here you can see that for lateral deflection, I section is fine, 1, but head section is 3.5. It means that it is quite high, 3.5 times I section. And you saw in the video that this head section, it did not fail, and I section twisted and deflected laterally as well. And hollow sections, you can see it has got quite high second moment of area in minor axis direction, similar to head sections, which is 3.5 times I section. And IT is twisting. This is torsional constant. You can find it out in section table. Now here you can see that for plate, for head section and for I sections, all of them, they have twisting ability of 1. And for structure hollow sections, you can see that this is 100, which is very, very high. It is very unlikely that tubular section or structural hollow sections, they will fail in buckling. We normally do not check their buckling. Now the real question is, if they are that effective, why don't we use rectangular hollow sections in place of I-beams? Why do we see I-beams all the time being used? And there are 2 reasons why we don't use them. Hollow sections are very difficult to connect with other members. You need specialized plates and other things to connect them with other members. This is one reason. Other reason is, for resisting vertical loading, you will have to provide more material. It means that it has to be 5 times, it has to have 5 times more area than I section, which means that it's not going to be effective in terms of resisting vertical loading. I could probably use rectangular hollow section, increase the depth, and use section like this. But again, it will have 2 webs instead of 1 web over here, and that will increase the material, which will increase the cost. Now this slide again shows lateral deflection and twisting, and if we combine both, this is termed as lateral torsional buckling. This is very important. You can see that we have this reduction factor key as vertical axis, and then we have lambda dash LT. Now we term it as LT. This is MPL over MCR. Key is equal to MBRD over MPL, which means that we use reduction factor approach in case of beams as well. We check the lambda dash LT to see that if buckling check is required or not. If the section is very stocky, if it falls into this range, beam is going to fail by its plastic capacity. It means that we do not require this reduction factor, because this reduction factor is just equal to 1. So it will not make any difference at all to moment capacity. So there will be no reduction in moment. We have another extreme, which is slender, and you saw these both in the video. In slender range, MCR controls, and the reduction factor is going to be less. So our values of moment are closer to MCR, elastic critical moment. There is a very heavy formula for MCR. But most of the practical beams, they fall into this category where you have 0.4 and less than 1.2. This is the intermediate range where beam fails to reach MPL and it fails to reach MCR as well. This is where we will try to find out key LT. So buckling is very important. It should be checked wherever the top flange of a beam is not restrained by attachment of a slab. Most of the time, in case of primary beams, we check it. So the design implication of not checking buckling is that we will be highly overestimating the capacity of the beam. So if we do not check buckling, for which buckling needs to be checked, then we will be highly overestimating the capacity because we will just be relying on MPL, which is the material failure. The limit to this lambda dash LT is 3. So Eurocode does not allow more than 3. So lambda dash LT, the limit of slenderness, is 3. This is the formula for MCR, which we will be using. E is Young's modulus. IZ is second moment of area in minor axis direction. And note here the absence of major axis dimension. There is nothing which is major axis. I can write this formula like this as well, but here you can see that there aren't any major axis parameters. So IW is a warping constant, which you can find from section table, and IT is torsional constant, which you can find from section table. LCR is the critical length. G is the shear modulus. E over G is normally about 1/3 of Young's modulus. So E, to be precise, E over G value is 2.6 and it is constant for steel. So you can remember that. This slide shows a similar pattern which I showed earlier about comparing different cross sections. This is very important.
The design procedure for unrestrained beams is pretty much similar to columns. First, we classify the section, and then we check if buckling check is required or not. And for this, we check lambda dash LT, which is equal to under root MPL over MCR. If lambda dash LT is less than 0.4, then no buckling check is required. We simply work out MCRD and we check MED over MCRD. This should be less than or equal to 1. If lambda dash LT is more than 0.4, it means buckling check is required, and then we check MED over MBRD, where MBRD is buckling moment, which is found out by reduction factor approach, which is equal to key LT WPL into Fy over gamma M1 for class 1 and 2 section. If it was class 3, then we will use W elastic. If it was class 4, then W effective. We use this formula to find MCR, where C1 depends on moment gradient, and for standard cases, C1 depends on load pattern. For a standard case of uniformly distributed load, simply supported ends, C1 is 1.132. For a central point load, simply supported beam, it is 1.365. We can then find reduction factor key LT using this formula, equation 6.57. Key LT is equal to 1 over phi LT plus under root phi LT square minus beta lambda dash LT. Again, this formula is very similar to what we used in columns. Phi LT here is 0.5 into bracket 1 plus alpha LT lambda dash LT minus lambda dash LT 0 plus beta lambda dash LT square, where value of beta is 0.75 and alpha LT is found out from table 6.5 and 6.3. For alpha LT, first we go to table 6.5 and we compare H over B values with the limiting values, and we choose a curve from here, and then we go to 6.3 and corresponding to buckling curve, we find value of alpha LT.
So for example, level of application of load. If the load is applied at the top, if it is applied in the middle, and then if it is applied at the bottom flange, there will be effect on the formula, and that would be taken into account with this factor, which is C2 factor. But again, I will not go into details of this and conditions for support, and there are various other formula. You can see that C2 times ZG, but I will not use this formula quite often, but this is just for your information so that if you need in some kind of situations, you should know that the information is there. Another key thing which I wanted to highlight is this LCR. There are various parameters for LCR similar to columns, but the most common one is LCR is equal to 1 times L. which is the situation when you have pinned connections at the end. Now here you can see that the first condition is fully restrained. This is the case when we use LCR is equal to 0.7, I think, 0.7 times L. You can see that the flange of the beam is attached with the column and with the help of extended end plate, and then you have these stiffeners as well that will prevent column from rotating. It means that the beam is rigidly connected to the column. And then we have semi-rigid connections. The typical examples are if we have full depth end plate, so LCR is equal to 0.8 times L. Finally, we have web cleats bolted to the beam and then again bolted to the column. Now, one thing that we avoid in case of unrestrained beams is the fin plate connection. So fin plate connection means that you weld a plate to the column and then you bolt it to the beam because it does not provide much torsional rigidity.
The most common simple connections are partial depth end plate connections.
So the most common one, if you're not sure, then it is LCR 1 times L. This is summary of MCR. And the question is, how do we determine this key LT? And there are two cases for finding out key LT. One is general case, which is not allowed in UK. So this method should not be used. 6.3.2.2. This is not allowed in UK. Details you can find in Eurocode 3. We use the one 6.3.2.3. And these section numbers are the same as you would find in Eurocode 3, which is for rolled sections and welded sections. Again, you have some other variation, but I will not go into details. Reduction factor can be modified using this formula to take into account effects of moment distribution, and there are different factors. So if you use these factors, it will give you more accuracy. If you stop up to this point, I would probably stop it. I will not use these details, but it is just for your information that these things are there. And again, it's modification. So C1.
There are many ways to work out lambda-LT. The most accurate one is using MCR. Lambda-LT is equal to under root MPL divided by MCR. You can also use this website CTICM and search for LT beam software. This will give you value of MCR rather than using this very long formula. The second one is from BS5950 old British codes, which is equal to lambda-LT is equal to lambda-LT divided by 93.9 epsilon. The easiest one and simplest one which structural engineers used is lambda-LT equal to L over 96 IZ. But this is only valid for S275 steel. For other types of steels, please refer to Extracts to Eurocode 3 guide, which is mentioned in the link down below. For S275 steel, lambda-LT is equal to L over 104 IZ. For S355 steel, lambda-LT is equal to L over 85 IZ, where IZ is radius of gyration. All design formula that I have discussed in this lecture can be found in this link bit.ly/steel design. Simply no sign in is required. Simply click on this part 1314 unrestrained beam. The yield strength, LTB resistance, reduction factor, everything is included in here.